today's class. Today, we're going to start talking about a special type of locally finite fundamental domains of Fuchsian groups. Namely, we are going to establish some basic properties about those locally finite fundamental domains that are convex, hyperbolically convex. Right? So all throughout today's lecture, I'm going to assume that P is a convex, locally finite fundamental domain for the Fuchsian group gamma. So recall that for any fundamental domain which is locally finite, convex or not, we can find for each point Z in the hyperbolic plane an open hyperbolic disk NZ containing it, and with the following two properties. First, that only finitely many elements of gamma have the property of making the topological closure of P in H meet such hyperbolic disk. And second, that Z belongs to the image of P bar on any given element of this Z. So recall how NZ, how one can prove the existence of this NZ. So one starts with the point Z, and one takes any compact neighborhood of this point. By local finiteness, only finitely many elements of gamma have the property of making the corresponding image of P bar meet this compact neighborhood. But for some of these images, it may be that Z does not belong to them. So what one does is, since it's only finitely many, so one takes a sufficiently small hyperbolic disk around Z with the property of avoiding each of the images which do not contain Z. So for this hyperbolic disk, only finitely many elements of gamma have the property of making the image of P bar meet this open hyperbolic disk. And because of the way we define this disk, for any image of P bar which meets this open disk, Z necessarily belongs to that image. Right? So that's very briefly why this open disk exists. Okay, so now let's show the following. So in this situation, if I take any element of the boundary of P, then there is some non-identity element of the Fuchsian group that takes it again to the boundary. And of course, in some cases where Z may be an elliptic fixed point, it may be that this one, despite being different from the identity, still sends Z to Z. Right? So that may happen. Okay, so for the proof, consider this set. Right? So certainly the identity belongs to this set, right? Because Z is in the boundary of P, right? So at least the identity is there. But if it had only one element, then it would be only the identity. But then we would have that NZ is contained in P bar, right? This open disk would contain in P bar. Why? Because these are precise. Because we have NZ contained in the union of over nu this nu of P bar, because P is a fundamental domain. So if only the identity belongs there, then we necessarily have this, right? But then you see, then we have our open disk around Z, completely contained here. So this means that Z belongs to the interior of P bar. But the interior of P bar is P again, and this is because P is convex and open. And this is a non-trivial fact. So this equality happens because it happens for Euclideanly convex sets, and so to prove it, one takes it for granted that it happens in Euclidean space for Euclidean convex sets, and then you work in the Beltramic line model to deduce this fact now for the hyperbolic plane and for open convex for hyperbolic open convex sets. So the theorem would be that if P is an open convex set, then it coincides with the interior of its closure. Okay, but if this happens, then Z is in P, but now you see it cannot be in the boundary of P. So it's kind of, this pretty much follows by counter positive, if you want. Okay. Now we have this lemma. For every non-identity element of the Fuchsian group, the intersection of P bar with its image under that element is either empty or a point or a shortest curve. It can indeed happen to be empty. How can this happen? Well, this is if gamma takes P bar very far away. Right? Or a point, how can it be a point? For instance, it may be that gamma is elliptic and has a fixed point in P bar. And let's say elliptic, I don't know, of order 5. And let's say that this is the fixed point and that this is P bar. Then when you consider the cube of gamma, you are more or less here. And so this is gamma of P bar. The cube, let's say, if gamma is elliptic. And then there you go. Then the intersection of P bar with its image under this element consists of just a point. And the third possibility is that it be a shortest curve, but that's it. That's all three possibilities. So let's prove it. So we need to show only that if such intersection has at least 2 points, then it is a shortest curve. That's what we have to prove. Now, because of this property and because the area of the boundary is 0, this intersection cannot contain 3 non-collinear points. Right, if it contained 3 non-collinear points, then you would have, when you take the convex hull of these 3 non-collinear points, that convex hull contains an open disk, and then you cannot have this. Okay, now this happens because we already showed that if you take a non-identity element of the Fuchsian group and a point in P, the image of this point under that element of gamma cannot lie in P bar. And that implies that this intersection has to be contained in the boundary. Okay. All right, but then you see this intersection cannot contain 3 non-collinear points, so all points in that intersection are collinear. But if they are all collinear, then it's because the intersection is indeed a shortest curve. Okay. Let's give some names. Right. So these intersections are going to be special, if only because, as we saw, the elements of gamma for which such intersections are not empty generate the whole Fuchsian group, for instance. Okay, so any such intersection is going to be called a gamma side of P, provided, well, of course, that this is not the identity of the group, and second, of course, if that intersection has at least 2 points, so that it's indeed a shortest curve. Yes. Okay, and then a gamma vertex is going to be any triple intersection. So somehow any intersection of one such set with another such set for different elements, provided it's not empty. Right? Okay, and then we say that it's a gamma vertex. Right? That such triple intersection is a gamma vertex. And of course, the first thing to prove is that any gamma vertex really consists of only 1 point, right? That it cannot contain more.
We have decided to call any such triple intersection a gamma vertex, provided it's not empty, and provided it arises from intersecting P bar with its image on their distinct elements of gamma, both different from the identity. So any such set better have exactly 1 point, right? So let's prove it. So take distinct elements of gamma, both different from the identity, and suppose that the corresponding triple intersection is not empty. So we want to show that it has exactly 1 point. So let's analyze what happens otherwise. Let's analyze what happens if it doesn't have, if it has more than 1 point. So let's say that it has 2 distinct points, W and Z. And well, first of all, notice that this is a convex set because it is the intersection of 3 hyperbolically convex sets. So together with W and Z, the whole shortest curve joining them is contained in that triple intersection. So this whole segment is contained here. Okay, now take any point in that segment distinct from W and Z. So take one different from W and Z, and take any point in P. Then the closed open shortest curve going from that point to this point that we took lies entirely inside P. And this is because because of the corresponding result in Euclidean convex geometry, which says that if you have an open convex set and you take a point in that open convex set and a point in its topological closure, then the straight line segment joining them lies entirely inside P, inside the original open convex set, except maybe for the point we took in the boundary, right? So this closed open segment is entirely contained in P. That's what the result in Euclidean convex geometry says. And we deduce it for the hyperbolic plane using the Beltramic line model, right? Like we did before when we proved that the topological closure of a convex set is convex. Of a hyperbolically convex set is hyperbolically convex. So a similar argument allows us to deduce that this hyperbolic shortest curve lies entirely inside P, except perhaps for this point here. Okay, now this happens for any point I take here, right? So what I deduce is that the hyperbolic convex hull of these 3 points lies entirely inside P, except maybe precisely for the shortest curve joining W and Z. So at least kind of all this region lies inside P. Yeah? This one maybe not. Most likely not. Right? But okay. All right. But so you see in particular on this side, when you consider the whole shortest curve, the doubly infinite shortest curve containing the segment that joins W with Z, and when you consider this side of that shortest curve, there are no points in sigma of P for sigma different from the identity. Okay, this will be important because now take a point now, let's say in gamma of P, and take again the shortest curve joining that point to an arbitrary point again here in this segment. Okay, and then again this closed open shortest curve lies entirely in gamma of P because of the same result that we deduced for the hyperbolic plane using the Beltrami Klein model. And so all of this, so the whole convex hull of W, Z, and this point lies inside, is contained in gamma of P, except again maybe and most likely for the original shortest curve joining W and Z. But then you see these forces this point and this point to be on actual to be like you see in the picture, namely on different sides of this shortest curve, right? On different hyperbolic half planes. All right, but then you see then I cannot keep going, right? I mean, if I take a point now in nu of P, that point is going to have to be on one of these two sides, and then I'm going to let's say that it lies on this side. Let's say this point in nu of P. But then you see, I'm going to get I must get some points that lie simultaneously in gamma of P and in nu of P. But we already saw that if gamma and nu are different, then gamma of P intersection nu of P is empty, right? So it is impossible to keep going, right? So what this means is that this being able to find two distinct points here must be impossible. So it must have exactly one point, and the lemma follows. This type of argument will arise again in some future arguments. Okay, so some lemma, a lemma with some that starts with some easy to prove facts, and ends with a kind of a harder one. Okay, so well, because of local finiteness, only finitely many gamma sides and gamma vertices can meet any given compact subset of H. Yes, of course, because any gamma side and any gamma vertex is of course still contained in P bar, right? I mean, you see, right? So still inside P bar. So if you give me a compact subset, then just from the fact that P was locally finite, it follows that that only finitely many gamma sides and gamma vertices can meet the given compact subset. Okay, so that's immediate from local finiteness. Okay, now a consequence of the fact that gamma is countable. So gamma is countable. So let's say gamma cross gamma is countable, and gamma cross gamma cross gamma is countable. So when you make those double and triple intersections, then you get only countably many gamma sides and gamma vertices. Right? So, right? I mean, for instance, take sets of this form. How many can we form? Can we, of this shape? How many can we form? Well, at most countably many things we can put here, right? So. Okay, and similarly with when you take triple intersections. Okay, so this is a consequence of the fact that the gamma is countable. Slightly harder to prove. The boundary of P is the union of all the gamma sides of P. Well, for one thing, something which is clear, I think, is that any gamma side is contained in the boundary, right? And that is because if you take only P intersect gamma of P, if gamma is different from the identity, this is empty. So this has to be contained in the boundary. Okay. And the converse for the converse, you take any point in the boundary, and for that point there is a non-identity element with the property of of sending the given point again to the boundary, and so Z is in P bar intersection gamma inverse of P bar, and you are done. Right? So it's on that side. Okay, and then every gamma vertex belongs to exactly two sides, doesn't belong to many, and lies on the relative boundary of each of them. So some words about this terminology. Given a shortest curve, which that shortest curve can be finite, right? It maybe it only joins two finite points, or it can be half infinite, or doubly infinite, right? So in either of those three cases, and we define its relative interior to be its interior when, instead of taking the whole hyperbolic plane as a whole space, we only take the doubly infinite shortest curve containing this. Okay, so for instance, in this picture that I just drew, the relative interior would look only like an open interval. Okay, similarly, define the relative boundary of a shortest curve to be its boundary when, instead of working with H as the whole space, you take the whole space to be only the doubly infinite shortest curve containing your original segment. In that sense, then the relative boundary of the segment I just drew would consist only of these 2 points. Okay. So the D tells me, every gamma vertex can arise only as the intersection of a gamma side with another gamma side, but you cannot have 3 or more gamma sides involved in the intersection. Okay. Again, a kind of a sort of dual is if you give me 2 distinct gamma sides, then maybe they don't meet. Right? Maybe their intersection is empty. That's perfectly possible. But if their intersection is not empty, then it is a gamma vertex. It consists of only 1 point. Okay, and finally, take any sequence of elements of gamma, and the statement is that the Euclidean diameter of the images of P on this sequence, that it always tends to 0, right? So somehow the idea is that the intuition is that this starts kind of converging to the converging when working with C bar and the topology of C bar. Somehow this starts converging the kind of the whole set to the circle at infinity, and so it really has kind of to shrink if we see it with an Euclidean eye. So that's kind of the intuition or an intuition. Okay, so as I said, A follows from local finiteness, B follows from the countability of gamma. For C, I already gave the argument, but I can repeat it actually. I mean, the easy part is that every gamma side is contained in the boundary. Okay, and conversely, the argument I gave before is valid, but also the fact that if you take a point in the boundary, then this set that we formed before, it cannot have only one element, because if it had only one element, that would have to be the identity, and then NZ would be contained entirely in P bar. So you see, so we would be back at in this back here, right? And then Z would not be in the boundary. Okay, for D, so suppose that I have a gamma vertex. Suppose that I have a gamma vertex, which then it has to be a triple intersection, right? So it has to be there have to be at least 2 gamma sides have to be involved, right? Because you must have P intersect gamma P bar intersect nu P bar. So you see, at least this gamma side is involved, and this other gamma side is involved. All right, but you see, you cannot have a third side, because if you had a third side, you see, you would have here some third gamma side. But then you see, then you have problems with these points, because then some of these points you could argue that they are both in the boundary, which we already saw that they are forced to be contained in the boundary. But on the other hand, you would be able to put them inside P. So you get a contradiction, right? So that's the reason why only two different gamma sides can be involved. And then in the relative interior of each of them, right? So let's say this. So suppose you take some point in the relative interior of one of these, then you can repeat the argument I said here, with which I deduce that I could not keep going beyond the gamma, to show that here you cannot go beyond, you see, P and gamma of P bar, and so you cannot arrive at, you cannot go beyond that. So this point in the relative interior of this shortest curve cannot be a vertex, right? And so the gamma vertices have to be in the relative boundary. That's how the argument goes. If two distinct gamma sides meet, they do so in a vertex. Well, I would say that's obvious, right? Two distinct gamma sides. Well, you have one, you have the other. Gamma is different from the identity. Nu is different from the identity. Right, but if gamma were equal to nu, then this is just the same gamma side as this one. Right? So it's obvious that gamma and nu are different. So indeed, if they meet, then they do so in a vertex. Okay, and F, I'm going to skip the proof of F. Okay, so this is some basics of convex fundamental polygons, and we will continue with some further properties next class.